And how many? Okay. Oh, I need to think. Okay. Hi, everyone. So just a reminder that not next week, but the week after, on Tuesday, it's the second midterm. Okay? So, wait, what's the date of that? 17th? 15th. Okay, so reminder. Midterm 2 is the 15th of November in class. As before, same thing as last time. You can bring cheat sheet if you like. It'll be the same kind of deal. I will release a practice midterm probably either like this week or early next week. Really. So.
Is it just going to be up to notes 11 or including exercises?
I think it will just be up to this. Yeah, so it'll be mostly stuff about the natural numbers and infinity and constructions of reals and stuff, and cardinalities. I don't know what I'm going to ask you. I can't even remember what the content is. I'm too sleepy this time of day to remember what the content is. All right, so what did we do last time? Let's remind ourselves by looking at the notes, because I forgot. Equinumerosity, finiteness. Okay, so last time, we defined this notion with this notation, which I read that A and B have the same cardinality. And this is true if and only if there is a function from A to B, which is a bijection. Okay, so and the way we're going to interpret this is that A and B have the same size, right, as sets. They have the same number of elements. So this aligns with what you think it means in the finite case, but it also works in the infinite case. So on top of that, we said A is finite if the cardinality of A is equal to the cardinality of n for some natural number, with the idea being that a natural number has itself many elements, right? 0 is the empty set, it has 0 elements. 1 is the set containing 0, it has 1 element. 2 is the set containing 0 and 1, it has 2 elements, and so on. So these are the finite sets, and A is infinite if it is not finite, which is not especially satisfying, but is a definition. Okay, and what did we prove? We showed that, like, omega has the same cardinality as omega times omega. We showed the reals has the same cardinality as an interval of reals, and that the power set has the same cardinality as 2 to the set, I think. So those are some examples. And the final theorem that I like half proved, because I proved it out loud, but I didn't write out, I wrote out some of the details, some but not all of the details, is that if, I don't know, f from n to n is an injection, then it is a bijection. Okay, so this little lemma here has a key corollary that we can start off with today. Corollary. Which is if A is finite, there is a unique n in omega such that the cardinality of A is the cardinality of n. Okay, so this is a very desirable thing. If we think that cardinality measures sizes, we want the size to be, and like we think that our natural numbers measure their own size, and this will be very desirable. Why does this follow? Well, because if there's two, right, if there's n and there's m, then taking inverses where necessary, you can get a bijection between n and m, right, by pulling through the bijection with a in the middle. But one of n or m is smaller, and so that means that the bigger one, there's a bijection to a proper subset of itself, and that contradicts this theorem here. So if there's two, one of them is smaller, and then the bigger one has a bijection with a smaller subset of itself, and we've shown that's impossible. Okay. So what we're going to do now, instead of writing cardinality of A equals cardinality of n, we're going to slightly, as I say, abuse notation. I'm going to say the cardinality of A is n. So why is this an abuse? Okay, so because this notation here says two things have the same size, right? But doesn't tell you what that size is. And in fact, I'm agnostic about even naming sizes at this point. We don't have enough theory to like give names to all the sizes. Here, I'm introducing a name for each finite size, right? Like the size 7 is named by our natural number 7, which is the set 0 through 6. And it would be very convenient to have names for all of the sizes, but that's actually quite hard. We have to postpone that till pretty late in the class. Okay, so anyway, we have this piece of notation. So if you're skeptical about like introducing names for sizes, this is abbreviating the version where there's absolute values here. But if you're not worried about it, then you can take it as literal. And one more corollary is that omega is infinite. So how would we prove that? Well, to show it's infinite, we have to show it's not finite, which means we have to show there is no bijection between omega and an element of omega, right, which is a natural number. So you'd have to show there is no bijection between n in omega and omega itself. And you can think about how you can prove that. This helps. Right, if it's finite, it has a size, and you show that's a problem. Okay, so when we have an intuitive notion like size that we're trying to give a mathematical definition of, you want to test that your definition is good by checking that things that should be true are true of your definition. So right, we have this definition of finiteness, which is pretty abstract, right? If you actually work through all of the right? It means we've got this abstractly given set omega and bijections and stuff. Okay, so some things that we'd like to know, for instance, is that a subset of a finite set is finite, right? It seems that subsets should be smaller, or at least not bigger, right? Maybe they're the same size. So if you have a finite set and I take some but not all of the elements, then you'd hope you're still finite. A finite union of finite sets should be finite, and if A is finite, then its power set should be finite. Those are all theorems that you might want to prove, and you can prove them all by induction. I don't even want to prove the first one. Are we okay? Like, trusting that there is an inductive proof. If you wanted to work it out, the details, you can. It's not too bad. So yeah, they're all proved by induction, and if you want, you can look at the notes. Because finiteness is only, if you want to do finiteness, go do discrete math. This is set theory. We want to do the infinite stuff. All right, so we'll go on to the next notes. Hooray. Control L. Zoom in. Ta-da. Okay. And that's the recall stuff that I just mentioned, and stuff about cardinality rather than being a cardinal. Okay, so here's my promise. Okay, so this is the promise the book makes to extend this abusive notation. So in the future, we will extend this little abusive notation to have a name for the size of every set. And so that works out, if we have two sets which have the same cardinality, then they better have the same cardinal, right? We better name them the set with the same size. Sorry, we better name their size the same thing. And our definition had better make this true, right? The size of a finite set is the corresponding natural number, right? And those things will be called cardinal numbers. So there's, unfortunately for me, a goy, the things that we use to name these are Hebrew letters, and I'm not very good at drawing them because I didn't go to Hebrew school. It's Cantor's fault. So that is my attempt at an Aleph. I apologize to Jewish audience members that I don't know how to draw your letters. This is the first letter of the Hebrew alphabet. This thing here, this is going to be the size of omega. And if the subscript here, if I increase it, right, Aleph 1 will be the next biggest, and then Aleph 2 will be the next biggest after that. And I have to show that there is such a thing, and so on and so on. But having names for sizes allows me to state theorems slightly faster. So instead of saying, if A and B are in bijection, then something, 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 I can say if two cardinals are equal, then something happens. So I just save myself a bit of time. And the variables that are used for cardinals are usually kappa, lambda, and mu. So like Greek letters from like the middle of the alphabet. Okay, so here's an example of me using that notation. This is me practicing to write the Aleph as well. It's even worse if I have to write Beth or Gimel, which look the same to me. Anyway, so cardinal arithmetic. All right, so we've got these cardinals. They're measuring sizes, and I want to compare them and combine them and measure sizes of other things based on those sizes. So firstly, I'm going to tell you how to add, multiply, and exponentiate cardinals. Okay, so if kappa and lambda are cardinals, then, and I also want some, boom, and I have sets K, that's a very bad kappa, K and L, which have the right size. So K has size kappa, L has size lambda. Okay, so firstly, cardinal sum. So the way I want to define this is how we learn how to add in elementary school. So if you have kappa many apples, and I have lambda many apples, and it's always apples, and I add them together, you pour the apples into a big pile, and that's how many you have, right? And pouring into a big pile, we have a notion of that, right? It's union. So the cardinal sum is going to be defined by taking a union of sets of the right size. Now, I have to be ever so slightly careful here when I'm taking this union. There's a small subtlety. Can you guess what it is? What is this? Yeah, I don't want overlap, right? They have to be disjoint, because otherwise I would undercount. So, yeah. As long as you didn't repeat elements, this works out. Sometimes authors use this, the symbol, it's usually this, like square union. It means disjoint union. And it means if there were repeats, then like make copies of the elements which are technically distinct and then take their union. And we could do that, but I don't want to have to introduce extra notation. So I'm just going to assume that kappa and lambda were disjoint. Okay, so that's cardinal sum. And cardinal product is, sadly, we no longer can use our apple analogy because I don't know how to multiply numbers of apples. But I don't know if this is intuitive or not. The size of kappa times lambda is equal to the size of the product of sets of the same size. That's how we're going to define these. So it's like I've put the set of size k on the x-axis and the set of size L on the y-axis, and I take all of the points in the corresponding like grid that I get, right? And that these hopefully should match with your intuition of what happens in the finite case, right? So if this is n and this is m, then I take a collection of size n and a collection of size m, and I make a grid, and however many points there are in the grid, that's the product, right? So they should work in the finite case. And then finally, exponents, kappa to the lambda. Now this is actually why the notation I use is different than the notation in the book. It's to make this look nicer. So it's the size of k to the L. So remember, k to the L is the set of functions from L to k. Now, it can take a little bit of you can take a while to check in your head that if these are finite, n and m, then this actually works, right? So n to the m is the number of ways of making m choices out of a set of size n, right? Which is the number of functions from m to n. Okay, so cardinal arithmetic, here's the definitions. What do I need to prove? Okay, so for these definitions to make sense, it had better not really matter what k and L were, just that their sizes were correct. Right? Technically, what's happening here, I mean, I'm not actually doing this on equivalence relations because this isn't a relation, but I've chosen sets of particular size to represent all sets of those size, right? So it had better not matter which choice I make. Okay, so to show if cardinality of k prime is k, cardinality of k, and the cardinality of L prime is L, then we get the same answers. Does that make sense? Right. So as long as k prime, L prime are disjoint, then k union L had better have the same size as k prime union L prime. Same for the product, same for this. Also, I've used the plus symbol and the times symbol and the exponentiation symbol. Well, I guess this I use cross for the multiplication of natural numbers, but I'm already tired of writing that, so I'm going to start using dots. We'd also have to check if these are finite, then they equal the version of plus a multiplication defined by recursion. Because otherwise, I'm using the same notation to mean two different things, and that's bad. So we'd have to check, for instance, that n plus m is equal to n plus f, where the pluses are in different uses, where this is cardinal sum, and this is recursion theorem sum, or like normal addition, as you would call it. Right, and so these are things that one would have to check, and I'm not going to, because I'm sleepy. So here's a theorem that says that. Proof, I'm going to make this homework. Hooray for me. So these aren't, well, not this part. This is proof by induction. But these parts I'm going to make homework. They are an exercise in moving bijections around. Okay, so they're good. It's good notational exercises. They're not like especially deep. I'm just going to keep using them as if we have. Okay, but what we are going to do, by we I mean you, is do this exercise. So I want you to try and simplify these cardinal expressions. So they are currently unsimplified. There is something to be done. So tell me, right, remember aleph null is the size of omega, right? And just in case that notation has disappeared from your mind, n is some natural number. Simplify those things for me.
Are any of these easy? We know the answer. I think some of them.
I think so. Yeah, there we are. If I look downward. No one's complained about my volume in the videos, so I'll assume it's fine. Okay. So, this first one. Hopefully it's the easiest because it's up top. So if I take, what's my simplify? Tell me. Sorry? Absolute values of omega? Sorry? That's true. Well, let's be careful. So it is equal to that. What do I have to be careful about here, though? They're not disjoint, right? That's the problem. So I need to disjointify them somehow. Okay, let's just do that. Let's tag all of the elements of this with something to make them different. And how can I, so this is now temporarily, this is the set A0 up through A n minus 1, right? So I've like tagged them. That's true, but can I simplify further? Tell me. Yeah. Oh, that's unfortunate. Right, the aleph null eats the n. And the idea is, right, 0 through n minus 1 go to here, and then n goes to 0, n plus 1 goes to 1, n plus 2 goes to 2, and so on, right? So we can explicitly define a bijection by sort of adding n in omega, right? And that gives you space. But this is like the homework 1, right? N people arrive at the infinite hotel. Yeah? So this one does end up being aleph null. Okay, what about times? Tell me.
It's also equal to aleph.
So why is this true? Let's try and interpret it through the lens of homework 1. N many buses have arrived, each of which have infinitely many seats, right? But we can still accommodate everyone, right? The idea, and you all explicitly gave me bijections, right? You'd send like 0 through n to like the k0 pairs, and then n to 2n minus 1 to the k1 pairs, and so on and so on and so on. So you could explicitly define a bijection here. I don't want to because I'm tired. Or you could draw a snake. Yeah. N plus n. Sorry, aleph null plus aleph null. So if I have a copy of the natural numbers, and then I have another copy of the natural numbers, but I'm pretending they're disjoint, so I've like tagged them with something, so I can remember, and I take their union. Can I list off all their elements one by one? Can I still like form a bijection? Yeah, right? Like you do 0 goes to 0 here, then 1 goes to 0 here, 2 goes to 1 here, 3 goes to 1 here. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? You bounce between the two of them. Right, now formally speaking, this means if I have two sets of size omega which are disjoint, then their union still has size omega, right? There's still a bijection. That's formally, but and you could prove that by building the bijections. Product. Tell me. It's also omega. So reason why is because we proved this one. This is the size of omega cross omega, which we already showed is the size of omega, which is aleph null. Okay, yes, indeed. Suddenly the kappa appears. Okay, so if I, so this is an arbitrary cardinal now, arbitrary size. I've added 0. What should I get out? I'd better get kappa, right? Otherwise, this is really bad notation. But what does this mean formally, right? It means take a set of size kappa, take a set of size 0. What's the only set of size 0? The empty set. So then you take your union, you don't change anything. So of course there's a bijection, right? It's the identity. Product. You know what this has to be, right? Because the notation tells you. Right, it has to be 0, because otherwise I wouldn't write it this way. But why? Right, well, take a set of size kappa, take the empty set, which is the only set of size 0, and take their product. How many pairs are there in K cross empty set? None, right? Because there's nothing in the second set to pair with. All right, so it's empty. Kappa times 1? Better be kappa. How do we interpret it on the level of sets? Take a set of size kappa, take a set of size 1. There's lots of choices. And then ask how many pairs are there in the product. So you have kappa in your first set, you have 1 thing in your second set, right? And so you've got kappa many pairs, right? There's an obvious bijection. This is where we get slightly, exponentiation is always slightly messier. Okay, so kappa to the 0. Tell me. Yes, okay, so this is the size of the set of functions from the empty set, right, which is the only set of size 0, to some set of size k, right? And how many such functions are there? There's 1. The empty function, right? Right? The empty set is a function because it is a set of ordered pairs where each x has a unique y, trivially. Right? So it's a function from the empty set to anywhere. Right? So that's 1. So that's coherent with our idea of to the power 0, right? Like that's equal to 1 in most cases where this makes sense. What about 0 to the kappa? Tell me. You'd have to think about it. So does this change if it's the empty set on the right-hand side here? So how many functions are there from the empty set to itself? The answer is still 1. The empty function. Okay, so this is the cardinality of the set of functions from some set of size k to the empty set. How many such functions are there? So remember, a function, right, is a set of ordered pairs of inputs, outputs. There are no outputs. So how many functions are there? Even, you seem to have an idea. 0, right? There aren't any. Unless kappa is itself the empty set. In which case, there's 1. The empty function counts. Right, so if there are any inputs at all, there's no outputs to pair it with, so I can't have any functions. But if there are no inputs, then that's okay. So this is actually piecewise. Okay, so for us, this is key. Well, I don't know if it's key, but it is true. 0 to the 0 is defined and equals 1 for us. I spent a lunchtime this week discussing with my colleagues if we could even think of a simple example. Right, this is, in calculus, this is an indeterminate form, right? You'd L'Hopital and stuff. But we were trying to think of any simple example of any functions where this does anything other than 1. except 0 to the x as x approaches 0. That's cheating. And it turns out that, this is a fun fact, completely unrelated to calculus. So if the limit as x approaches a of fx is 0, and the limit of x approaches a of gx is 0, and f and g are analytic at a, then the limit x approaches a of f to the g is 1. So analytic means can be expressed as a power series. So it's actually very hard to think of pairs of functions where this doesn't go to 1, except the trivial case where f is the 0 function. This is not set theory. I just thought it was a cool theorem, and it was why it was hard for me to think of an example. And I had to do like e to the 1 over x squared, minus 1 over x squared, and get some stuff which doesn't have an analytic expansion. E to the minus 1 over x squared. It's not analytic at 0 because it's not even defined there, but it does have a limit. And even if you extend it to be defined there, it's still not analytic. Fun facts. Okay. So I like cardinal arithmetic because it's kind of funny, right? A key thing about cardinal arithmetic is that like cancellation is not true. And this is what I mean by cancellation, right? Like so cancellation says like if a plus b equals c plus b, then what do we conclude? A equals c, right? We cancel the b's. This is not true here, right? Because like 1 plus aleph null is equal to 2 plus aleph null. But 1 is not equal to 2. Right, so cancellation is false. So that's cool, well, I think. It's true in the finite, where everything's finite, it's true because it's, where it's finite, it equals normal plus. And cancellation is true of normal plus. But as soon as you involve infinite stuff, some stuff breaks. However, a bunch of stuff is true. In particular, these operations are commutative and associative, the way you'd expect. Multiplication distributes, as you would expect. And the laws of exponents are true. Just the cancellation is false, that's all. So cancellation is, in a certain sense, talking about subtraction, right? And what this is saying is there's no good notion of inverses for cardinal. There's no like cardinal subtraction. There's no cardinal division. Oh, I left these blank. Damn it! Now I have to write them out. Okay, so kappa plus lambda. Commutative means I can do it in the other way, right? Lambda plus kappa. Right, so that's addition is commutative. Same is true for multiplication. Associativity is that you can rearrange parentheses. That isn't a very good kappa, is it? If anybody is Greek and doesn't like my pronunciation of your letters either, I'm less sorry than I am to my Jewish students. It's just part of being from Europe. I just don't care as much. C'est la vie. There we go, so in French as well. Kappa times lambda plus mu. That's kappa times lambda plus kappa times mu. Right, and then there's laws of exponents. So I hope that these are what you would expect. Kappa to the lambda plus mu, that's equal to kappa to the lambda times kappa to the mu, right, and so on. Can you fill in the rest of the blanks? Okay, so these are all facts about cardinals, right, and what they, underneath the notation, what their claims are about sets of certain sizes, right? So what this says if K has size kappa, L has size lambda, and they are disjoint, then it doesn't matter what order I take union in, right? They're still in bijection. In fact, they're equal here. Same here. If I take the union of two sets and then union of a third, that's the same as taking the union of the last two first and then unioning the first. So these claims are very obvious for plus because it's get equality. But for multiplication, it's not entirely, they're not trivial, right? So K cross lambda as a set is not equal to L cross K, usually. But they are in bijection. The bijection swaps the order of the coordinates. Right, so that's how you would prove some of these. These get messy, right? So this is like the set of functions from L union M, mu is M, right, to K. And you have to say, okay, that's the same as the pairs of functions where one is from L to K and one is from M to K, right? And so they get harder to interpret. But they are exercises in moving bijections around. Okay, so that's cardinal arithmetic. Let's take a break, actually, before I do cardinal size, because that's where the good stuff starts. It's break time. What?
Okay, came with it.
No, I think
Got the little
Tuesday, but not
thread.
catching the
Thread as well. Because sadly it's an affectation. I guess it would be an affectation if that's manufactured.
I don't know what affectation.
Stop playing lexicon for today.
Okay, great to speak from an artificial design.
There you go. Yes, indeed. I'm a smart guy. Sorry.
That's its actual class. In boxes, they like fall in the cracks. So this was like it's happening. On my bar, I went to the contract over cracks. You felt was that.
Yes, indeed. Okay, yeah, so uniqueness is part of the sort of thing. So at least one of them is true. Okay, so what you want to do is take two reals which are distinct. You show one of these
Show either, or one of these, like either. Oh, right.
So assume they're distinct up front. Exclude one of the cases and then prove
So I
that
went to.
one is less than the other, which means one is a subset.
I don't know if there's items and it's a process, but I want to select there's details and so on.
Straight. Like if they're distinct, they're not equal.
Especially if I just say like.
So that's true. And I think one of the reasons why that's very intuitive to you is you're probably already thinking of the real is the set of rationals less than it.
Right.
But actually, this real is it's just a thing I'm calling it down. So it's a set with certain closure. So if they're distinct, then there's a rational that say is in X but not Y.
Right.
And then you have to show that Y was a subset. So just like go to the level of definitions. Like, what does it mean for something to be in Y? And like, how can I move that over to being in X?
Got it. And then when you use the person, okay, thank you. What are you doing? Oh, that's really nice.
Yes, I'm not.
That's so funny. Oh my god.
What about you? How is yours? Yeah, I honestly didn't plan it that far in advance either. Like, really, barely ordered anything, and like was able to really scratch about. Like, but I only bought. I ended up buying a pair of sunglasses, and, which is kind of awesome. Yeah.
Yes, you have to cheat by forcing them to be distributed quickly.
Yeah.
So you can do very simply,
Spheres.
which is,
He's like
but I mean, this works in the general case as well. So you define A, kappa,
That's the
lambda, then you define kappa plus lambda to be size of A cross 0 union L cross. So I've made them disjoint now, right? In a stupid way. That works all the time.
Christmas tree in front of it was delivered yesterday.
But then you have to deal with these. If you prefer this, that's fine. Use it in your groups.
Yeah. That's so funny.
Oh, that's right. That's what she did. She did an active radio. Or like yeah. I hate it so much. I forgot I had to do this.
Yeah.
And I got a text from Lily and like a month ago. She was like, oh yeah, can I do this? I was like, fuck, I'm still doing this.
Louise was my earlier.
Yeah, and she also wanted to do that. But like I fully forgot I was still on it. Like I'm not in the group chat. I was in the group chat. I was, but because I never. No, I don't really care. But I never was. So I was like,
I have something today.
yeah, there's so much drama.
And then
It was so bad. I must be
I
like.
have Monday, Tuesday, Wednesday, Thursday.
You want me to do?
Yeah, no, I don't have them in my head. They're in my calendar. I look on Cam.
But
Very
oh,
well.
okay. I can't do it.
Okay, yeah.
So you're like officially like who's the Alex Boy? Yeah.
I think.
Yeah.
Okay, well, I will look for you at 3, but if your surprise events occur,
Which was
So I
I missed.
No.
it's 4 O's. Oh, that's not very, I'm right next door to anyone, so if you went to there, you would.
She was on the-
Yeah,
That's literally I was just thinking that's literally what she's like, oh she applied to like the 3 most popular roles. She applied to the
Okay. Okie dokie. So, what do I want to say? Okay, so cardinal sum and product are actually trivial operations because if one of your cardinals is infinite, then the operation always just gives you the max. You do need the axiom of choice to prove that, but it is true. However, cardinal exponentiation is the most terrible operation of all time. Like, the size of this, 2 to the aleph null, right, if you think about it, this is the size of 2 to the omega, right, which is the size of the power set of omega. Right, so this is a set that's actually quite familiar to us, right, power set of omega. This is not determined by the axioms of set theory, even all of the ones, including the ones I haven't given you yet. This can be almost anything. Continuum hypothesis claims this is equal to the next one, aleph 1. But that claim is independent of CFC. This can be as large as necessary, or as you'd like. It can't be literally anything. There are a few cardinals it can't be, but it can be arbitrarily large. So yeah, cardinal exponentiation is a very badly behaved operation for the infinite thing. It's bad when the exponent is bigger than the base. The other way around is usually okay. But yeah, if the exponent is bigger than the base and it's infinite, then we're in a very bad situation. Yeah, there's something called, I think it's Easton's theorem, that says like this operation, like just 2 to the kappa, like it has to be like monotone, meaning if I plug in a bigger kappa, the answer can't be smaller. And it has to satisfy some very, very weak other inequalities, but otherwise it can be anything that's consistent with some very weak assumptions. Strange operation, badly behaved. So we don't speak of it very much because it's really hard to compute. Question? I think Easton? Theorem? Don't quote me on that. To someone else. I can look that up. If it's not that, I will have, for next class, I'll have you the real name of it. Okay, so, okay, but to talk about those, I just talked about things like cardinals being bigger than other cardinals, right? And there's a natural sense in which for finite cardinals that makes sense. And it seems that like the cardinality of omega is bigger than all the finite ones, but I want a better, more robust notion. Okay, so the way we're going to do that is using functions again. So we're going to define cardinality of A to be less than or equal to the cardinality of B if and only if there is an injection from A to B. Right, so the idea is we're doing this to measure sizes of sets. We like pair off elements of the sets using a function. And if our function is injective, we don't run out of elements of B, right? Every time you give me an element of A, there's another element of B I can pair it off with. But because it's not I don't assume it's a bijection, there could be stuff left over. So we're going to interpret this as the size of B is not smaller than A, greater than or equal to. Strict greater is if you're greater than or equal to and not equal. So unsatisfyingly, that's A is strictly less than B if A is less than or equal to B and A is not equal to B. Sorry, cardinals everywhere. You can translate that into the functions. This means there is an injection from A to B, but no bijection. Right? So all such injections are not surjective. This, it could be a surjection. I'm just not assuming that it is. And okay, so this is not a relation because it's too big. The set of cardinalities is not a set, so it's too big. And also something called Skolem's paradox. No, is that Skolem's paradox? No, that's a different one. I can't remember what the name of this paradox is. Curses! Yes, exactly. There's some paradox. If it's like the set of all cardinalities would itself be a cardinality, and then it would be in itself, and you could prove that cardinalities can never be in themselves without even the axiom of foundation. That's the paradox. But I can't remember what it's called, which is very annoying. All right, so as before, I'd have to show you that if I picked different sizes of the same cardinality, then I get the same result, right? So if A prime has the same size of A and B prime has the same size as B, I'd want to show you that there's an injection from A to B if and only if there is an injection from A prime to B prime. You can draw a diagram like this. What am I doing? What in the world? A prime, B prime, right? And so there's bijections here. And if you imagine there's an injection here, can you start here and get to here injectively? And if you go up injectively, then over injectively, then down injectively, you have a composition of 3 injections, which is an injection. So like this is actually well defined. So the proofs of these, as I say in the notes, are you move bijections and injections around in a circle until you are done. These are not especially deep proofs, but they're not bad to practice. But I just don't want to do them here because I've got a much better theorem coming up. Okay, so I've used this symbol here, less than equal, and this symbol here, less than. So that is suggestive notation, right? Like, so I'd better prove that the things that are suggested are true, or at least discuss how they fail. So the things we'd want to show, is number 1, the less than equal is reflexive, whatever that means. Strictly, I want to show that a cardinal is less than equal itself, right? Or if you prefer, the size of A is less than equal to the size of A. If you prefer to instantiate with a particular set. I'd want to show that it's transitive, right? So kappa less than lambda less than mu implies kappa less than mu. These two are easy. What is an injection from A to itself? The identity, right? The identity. It's in fact a bijection, right? So if I've got an injection from K to L and an injection from L to M, how do I get an injection directly from K to M? Tell me. Compose them. Composition of injections is an injection. Okay, so these are very direct. Great. Now, less than equal has a fun property. If kappa is less than lambda, and it's less than equal to kappa again, well, of course, kappa is less than equal to kappa by transitivity, but we know more. This is something called antisymmetry. This implies kappa equals lambda, right? If I can trap you between the same thing above and below, then you're equal to that thing. Antisymmetry. And then 4, I'd want to prove everything is comparable with everything else. So this is like totality. Okay, so these axioms, so this is reflexivity, transitivity, this is called antisymmetry, this is called totality. These are actually the axioms of a non-strict linear order, right? I've defined linear order for you to be a transitive relation which is trichotomous. That's the strict version. If you like the non-strict version, this is actually an axiomatization of that. Yes, Rudy?
Repeat number
3
3 again.
says if kappa is less than lambda, but which is also less than kappa, then it must be the case that lambda equals kappa. Right, so this isn't even possible in the strict case, right? Because then kappa is less than itself. But because we're allowing equality, this is allowed. Okay, this theorem has got its own name. It's that hard to prove. It's called the Schroeder-Bernstein theorem. We're going to prove it because it's one of my favorite things. And the next theorem, that all cardinalities can be compared, that's actually equivalent to the axiom of choice. So if the axiom of choice is not true, then there must exist sets A and B so that there's no injection either way, which is very strange. Right? Because it seems like you should start building an injection from one to the next, and either you succeed or you run out of elements on the right. But if you run out of elements on the right, turn those arrows around and you have an injection going the other way, right? Like that's what it seems to, and that seems to be a theorem that you could prove. But the problem is that if you're trying to build by just taking an element of A and pairing it with B, take a new element of A and pair it with B, I'm making choices. And if I don't know how to make those choices, and there's infinitely many of them, then I need the choice axiom.
Anyway, Schroeder-Bernstein. This has other names as well. So it's called the Cantor-Bernstein theorem or the Cantor-Schroeder-Bernstein theorem. And I think that Schroeder should probably have an umlaut, but I forgot to check, and I also forgot to put it in, so I might be misspelling it. Okay, but I want to prove this theorem. Now, I want to prove this theorem that the proof of it seems like one of those things like, how would I ever think to do that? Who is this genius? But I'm actually going to try and prove it to you in a way that I think you could have thought it up yourself if you had enough time. Okay? That's my hope for today. So our theorem is if there are injections F from A to B and G from B to A, then there's actually a bijection between them. Okay, that's our claim. Let me draw some pictures. Okay. So if I draw this picture, there are more things in A, assume. And there are more things in B, also assume. Okay, so there will be a bunch of arrows, right, in this diagram, right? This one will have a blue arrow, like going over here, right? And this one will have a blue arrow. Let's do something like that. Okay. And then there'll also be arrows going the other way, right? So maybe this goes this way. Okay, so because these are injections, we know blue arrows that start in different places end in different places, and the same for the red arrows, right? So what I want to do is pick some of the blue arrows and some of the red arrows and then turn them around and then somehow get a bijection. So what I mean formally is I'm going to use F on some of the elements of A, and I'm going to use G inverse on the other elements of A. And hopefully, if I pick the right choices, I can do so in such a way to get a bijection out. That might be like what you would hope, that I don't have to create any arrows that are not already there. Right? Maybe this theorem, the way you prove it, does not require you to use the arrows that are given by F and G. You have to build a whole new function, right? That's a hypothetical possibility. But if we're trying to prove something and we don't know how to do it, we could at least hope for the good case. Okay, so we're going to hope that we can define some function h which uses F sometimes and uses G inverse sometimes, and then we just have to work out what these conditions are. That's our hope. Okay? So, what we're going to do now is, assuming this works, what are cases where I know I either must use F or must use G inverse? Like, where do I have no option? So I'm going to erase these. You can draw another copy of the diagram, and should, so they don't get messy. Okay. So the first observation is if I want to use G inverse of A, then this has to be defined. Meaning, it must be in the image of G, right? So anything not in the image of G, I have to use F, right? There's no other choice. So if over here
everything here is the image of G. Another way you could write that is G square brackets B. Okay, so this stuff, I don't know. Maybe I can use F, maybe I can use G, because there are arrows going in and out. This stuff down here, though, there's only outgoing arrows, right? So what I'm going to do, I'm going to call this C0. So formally, C0 is the set A minus the image of G. What we know so far is I must use F on C0. Okay, and then maybe there's some wiggle room up here. I don't know what I'm supposed to use yet. But now I've made some choices over here, but this actually restricts choices up here in the following way. Get out of here. So let's say we've got something in C0. We know this goes over here somewhere, right? Via F. Now, where does the red arrow, G, coming out of here go? Well, it goes over here, right? But does it go above or below the line, or could it be both? It must go above, right? Because this is the image. There are no red arrows into here. Okay, so this goes over here. Okay, so here is where G takes this. Where does the blue arrow go from this guy? It just goes over to the right, right? Because I haven't given you anything to divide. Okay, so this guy here, who's in the image of G, if I'm trying to do this, I have two choices, right? I can either use F or I can use G inverse. But I can't use G inverse anymore. Why? Because I'm going to make an injection. And if I choose G inverse, then this guy and this guy both point here. Right? And that's not allowed. Okay, so that means because this one I have to use F, then I cannot use G inverse, so I must use F. Right? Complicated. And then that same argument can repeat, right? There's a red arrow coming out of here, going over here to a new guy. This new guy has a red arrow coming in and a blue arrow coming out. But I can't use the red arrow anymore, because that would be failing to be an injection, right? Because then this guy and this guy are both pointing here. So you can iteratively say, okay, I must use the blue arrows here. Yes? No, that's an equal sign. It's a vertical equal sign. G of B. As it would be pronounced. Okay, so the idea is, right, so this stuff at the bottom, we must use F. And then the things over here, which are the image of those things, we must also use F. That creates a new thing. We map its image over. We've got to use F there, and so on. Okay, so we can formalize this idea. All right, so we've got C0 over here. On C0, we know we've got to use F. Let me write this up here. Sorry, square brackets, square brackets. So everything that was in C0, it has a corresponding thing in B. So let me define a set of such things to be D0. So that's going to be F, the image of C0, which is, if you unravel, is F of G of B. Yes, what's up?
So is C0 the...
Oh, sorry, image... Yes, very key. Thank you. Yes. It's the complement of the image of B. That's very important, thank you. most key observation that was ever made. Do not take the complement of the set that I mean. Yeah. Okay, so we start with C0. Okay, so D0 are the things that this guy maps over into, right? So this is over here. This is D0. D0 has a corresponding image in A. So this is going to be G of D0. And everything in G of D0, we must use the blue arrows on, right? Because we can't use the red arrows because they're already used up. The value of the pre-image of the red arrow is already used up. So then let C1 be G of D0. So we've got to use blue arrows here. We've got to use blue arrows here. But then, every new thing I've used the blue arrow on, look at its image under F, and then its pre-image under G, then its image under G. Then I've got a new set of things which I cannot use red arrows on, so I must use blue arrows. And you can repeat this inductively. Am I getting... Oh, for G, then F, yes. So then Cn plus 1 is going to be G of Dn. And then Dn plus 1 is going to be F of Cn. Look at me proving this without notes like a genius. I did it yesterday in great detail, which is why I can do that. Okay, so what's the idea here? Must use blue arrows here because there are no red arrows. Then the things those point to, I can't use red arrows pointing to those. Which are the things with red arrows pointing to those? These things. So I must use blue arrows here. If I've used blue arrows here, those point to things which have red arrows coming out of them. I cannot use red arrows there, so I must use blue arrows. That's C0. And so on, and sorry, C2, and so on, and so on, and so on, and so on. Okay, so just because of where G inverse is defined, we know for free that we have to use F on all of these. Maybe other places as well. But at the very least, these. Otherwise, we will not get an injection. Yes, Rudy?
Bottom right, should that be
Yes, it should. Wow, everybody is really alert today. You're catching all my typos. Yes.
Is that top equals F of the image of the...
Oh, yeah, because I messed that up. Yeah. No. You're correct. F of C0, which is F of A set minus G of B. Okay, so what have we learned? So we have to use F if A is in the union of the C's, right? If we're in any of the C's, then I must use F. Okay, now we're going to hope. Does this work? Okay. So there, I think, theoretically, if you're trying to prove this theorem yourself, there's no reason to suppose that this is good enough for free. All we know is that at least this has to be F, and maybe some other stuff has to be G. But this is like the very minimal things that has to be F. And so maybe if we try and show that H is a bijection and we can't, then we can construct an example, write down, actually compute what this is, see where it breaks, and fix it. And then go on, and like this condition maybe gets more complicated. Turns out, by magic, this actually works, which is insane.